My question pertains to modularity, which is inherent in every SMR design. To this end, what compromises were there, if any, between modularity and the power and size of your design? What were the key considerations that influenced your decision in the size of your design?
Okay, I'm Song Danrong from Nuclear Power Institute of China. We developed the SMR named ACP100. The electric power is 125. When we select the power and the modular for this kind of SMR, firstly we consider the safety, the lower source term of such a kind of power, and secondly we consider the mature of the equipment. The major component of our SMR is for example, the reactor vessel, the one-through steam generator. We consider the technical readiness level for this component. When we select this component, we consider this kind of SMR can be built in near term. I mean, the near term may be less than 5 years. What we consider the size, the power of the SMR, and when we consider our design. Thank you. That's all.
You were very quick. Thank you, Mr. Song. Monsieur Salha?
So the question for us, it's not a question of compromise between modularity and power. In fact, it's a question of optimization. What we have tried is to have a very compact design. Everything is included in a reactor vessel the size of a 900 megawatt vessel. Everything, the core, the steam generator, the pressurizer, the pump. And on top of that, we have a relatively high level of power, around 170 megawatt electric, that's to say roughly 570 megawatt thermal, which make it possible to have at the same time a very compact design and a very high level of power. So no compromise, but rather a global optimization.
You are very quick and very precise. Thank you. David, your turn.
So good morning, I'm David Powell from GE Hitachi. And before answering these questions, can I briefly introduce our two SMR designs? So GE Hitachi has been designing, building, fueling and servicing reactors for over 60 years now. And our two reactor designs, one is called the BWR X300, which is a direct descendant from the ES-BWR design, which has already been through US NRC approval. And the other design is called PRISM, which is a Generation 4 sodium-cooled fast reactor technology. Both of those designs are around 300 megawatts electric output. And trying to answer those questions, our approach has really been about an overall design philosophy, which is really based on four main considerations. And those are really safety, simplicity, cost, and proven technology. So it's making use of all of those to get to that right level of output that we see available from our designs and required from the market today. One of the key aspects of those is, of course, safety. And in regard to safety, that's really taken as read as a ticket of entry into the SMR market. There's really no compromising on that. And that's really a key aspect of our design philosophy. In terms of really the modularity, we're one of the few vendors that's been actually building reactors that are based on modular build. So our alliance partner, Hitachi GE, has successfully built the ABWR using open-top construction and modular techniques for the last 25, 30 years. So we're one of those vendors that has real experience in how to design a plant with modulars built into it. And that's really the key, is actually design the plant from the very first steps to be able to introduce modules in there.
Thank you, David. Mr. Song?
Good afternoon. My name is Jae-Seung of Song from Korea Atomic Energy Research Institute. The answer for the question is, SMART is based on the standalone design and has twin design basic model. The output per unit, 100 megawatt electricity and 40,000 tons per day of seawater desalination, is based on the energy and water supply for about 100,000 people. SMART is an integral type pressurized water reactor which installs the major components inside the reactor vessel so that no large pipe is required to connect reactor, pump, steam generator, and pressurizer. Therefore, large size loss of coolant accident, which is one of the most limiting accidents in pressurized water reactor, can be excluded. The diameter of a SMART vessel is based on the maximum possible manufacturing in Korea, especially the capability of Doosan heavy industry. The height is determined by the fuel length, steam generator installed inside the vessel, and the top and bottom heads. One of the critical parameters is the height of steam generator, because SMART uses the conventional control rod drive mechanism installed at the reactor closure head. The steam generator tubes should be located outside core support barrel, and that the control rod extension shaft located is inside. For the space efficiency, SMART uses the helical type once-through steam generators. The tube curvature at the innermost layer is limited so that the in-service inspection probe can move inside the tube. The height of steam generator is determined by these considerations. Thank you.
Thank you. Tom, your turn.
Thank you. Hi, I'm Tom Mundy from Nuscale Power. It's important to appreciate our technology and what it's based upon. The heart of our technology is called the Nuscale Power Module, and that's an integral reactor vessel, steam generator, pressurizer, and reactor core all in one vessel, surrounded by its own high-pressure steel containment. And the underlying features associated with our technology in deciding the right size composition of the plant was safety, scalability, flexibility, and an economic proposition. And we're probably one of the most advanced technologies, certainly in the U.S., in terms of design development. We're undergoing a review by the NRC, U.S. Nuclear Regulatory Commission, currently, in which we'll see their approval of our design in 2020. Safety case has to be second to none, and in fact our technology demonstrates that in fact it is second to none in terms of its safety performance. The scalable aspect, though, we wanted to be able to give a generation solution that allowed the clients to add 60 megawatts of capacity with the introduction of a subsequent power module. So each of these power modules is connected to its own power conversion equipment. Steam turbine generator, it makes 60 megawatts of electricity. Every time you add a power module in the facility, you're adding 60 megawatts of capacity. While these individual modules produce 60 megawatts, the total facility output can house up to 12 modules is 720 megawatts. So a fairly substantial, large generating facility, but the safety case presented by a very small core, 200 megawatts thermal of power produced. The flexible aspect, we wanted to do more than just produce an electricity solution, a baseload electricity solution, so the technology has to deliver additional features and capability that the current plants do not offer. So it's the ability to provide process heat, it's load following capability, it's a number of resilient aspects of the technology that you don't find in other technologies. And then lastly, it had to present an economic solution. So we have to be competitive with not only advanced nuclear, but even with combined cycle gas. And therefore, we sized the facility to provide, with the megawatt output, to provide that economic perspective, and also to focus on the repowering of coal, primarily retiring coal in the U.S. If you look at most of the plants, more than 80% of the plants that will coal plants that will retire in the U.S. between now and 2040 are somewhere around 300 to 600 megawatts. So we wanted to provide that kind of repowering solution to our clients to consider a Nuscale option as that repowering feature.
Much, Tom. Alan, your turn.
Thank you. Good morning, everybody. I'm Alan Woods from Rolls Royce. I'll answer the questions in reverse order. So the key consideration that influence the size of our design. Our design is, first of all, it's not just a nuclear reactor. We've taken the approach that this has to be a power station design. We often in the nuclear industry get obsessed with the reactor technology, but in customer terms, the reactor is only about 20% of the total capital cost. Therefore, we have to look at the power station. So our approach has all of the necessary partners to bring all those capabilities together. What drives the power is quite simply the requirements set of our design. It's requirements driven. We have to access sites. We have to be road transportable for an SMR. We don't want to put bottlenecks into the supply chain. And all of those combination of requirements drive the maximum size of our reactor pressure vessel. And that maximum size drives the maximum amount of conventional fuel we can accommodate, and that drives the power output. We did not design the plant around a specific power. So in terms of compromises between modularity and power, it's already been mentioned. Our approach is, it's not a compromise, it is about optimization, and that optimization has to be driven by cost, by the LCOE. Our approach to modularity is slightly different. We don't see modularity as a design in itself, it's a solution, and it's a solution to a fundamental problem, and that one is one of cost. Modularity has to be a solution of bringing down manufacture and construction cost. Equally, we have to look at modularity across the whole power plant. I mentioned earlier, if we just look at the nuclear island, we can modularize that as much as we like, and we bring down the cost of that as much as we like, but at 20% of the capital, it's not going to make a huge amount of difference. We have to modularize the whole power station. So our approach is exactly that. It's having modules which are sized around optimizing the cost of the modules. That means we don't put too much cost into facilities, and it's about modularization of the whole power station, including the civils.
Thank you very much, Alan. Anton, you're last.
Good morning, everyone. I'm Anton Moskvin from Rusatom. And let me start with a couple of words about Rusatom to explain what considerations we influenced, as it was in the question, influenced our decision on the design. Rusatom have the long history. We are developing nuclear technologies for more than 70 years, and currently we are the largest nuclear technology vendor on the market. So through our history, we elaborated several different designs of the small, medium, and large-scale capacities ranging from several megawatts to more than 1,000. Our first modern small modular reactor we decided to put on the floating base, and the ship Academic Lomonosov, the power plant, floating power plant Academic Lomonosov, will be commissioned in 2019, next year. So as we have had several options, design options to develop, we worked on the concept of small modular reactors, starting with the market analysis. And we figured out that 50 megawatt might be or shall be the most marketable capacity. And this lets us work with a wide range of customers, ranging from the countrywide grids to some commercial applications, commercial consumers or standalone facilities. We may use this capacity within the limited grid infrastructure. We have ability to scale up this capacity by adding modules and using maximum effects of modularity. So our current upgraded Rhythm series reactor is the Generation 3 Plus. It's the modern reactor which have a reference on the which have a technology reference on the icebreakers which we are using currently. We have 6 nuclear reactors of this design already produced, and 4 of them installed on the icebreakers. So I agree with my colleagues that there is no need to compromise on modularity when we talk about the small modular reactors, as it shall be the integral, as it is an integral part of the design. And of course, we have natural limitations for scaling this capacity up by adding more and more modules, and we think that the natural limit here is 400 megawatt. On the other side, we tackle this issue of this modular limitation by having a different design of 600 megawatt. We think that this is a different, it shall be a different design for a different market sector, which is a medium capacity, nuclear power plant sector.
Thank you, Anton. We are almost on time, not very well, gentlemen. So we are going to question number 2 from Jae-Seung, CA.
We all know that nuclear deployment worldwide needs a strong demonstration of safety, a full compliance with the best safety standard. These are the major conditions for large public acceptance. So I have a few questions. Usually people say that small is beautiful. Could you say that small is also safer in the case of your design, and why? In a deterministic approach, accidents happen. Most Generation 3 reactor design integrate this principle and target zero leakage outside the nuclear building. How does your design master the environmental impact in case of a severe accident like what happened in Fukushima or worse?
So we're not always going to start with the same one. So Bernard, would you like to start, please?
Let me say perhaps a few words first of the French consortium. I didn't touch any word about that before. So we are building at the moment the design of a French SMR on the basis of the experience of 4 main partners who are CA, Technicatom, who has a big knowledge in small modular reactor, Naval Group, the former DCNS, marine operator, and of course EDF. So perhaps to answer the question of Jae-Seung about nuclear safety, the main feature perhaps of safety in our design is the global integrated architecture. I mean that, as I said, everything is a unique reactor vessel, which means that the size of LOCA is almost excluded. LOCA are almost excluded. We are also forecast internal CRDM, which make operation easier, and our reactor is boron-free, which means that the dilution accidents are eliminated. On top of that, because of use of passive system, we have a very long grace period of 7 days. It means that operators may wait up to 7 days before operating, bringing additional electricity, additional power, and additional cooling. And for core meltdown, in fact, we have taken the concept of in-vessel retention for the corium.
David?
Okay. So let me try to answer these in order. Both the BWRX-300 and PRISM are passively safe designs. They're based on our design philosophy that safety can be achieved through simplicity. So, as you're probably aware from a BWR design, most of those steam components are contained within the reactor pressure vessel. So again, that's helping to control those safety requirements. The BWRX-300 is based on our ES-BWR design, which has been approved by US NRC and has the ability to cool itself for 7 days without the need for operator intervention or AC power. The BWRX-300 is the same. So we have that same passive capability in the event like Fukushima as referred to in the question. But also in designing the BWRX-300, we have also taken a path of eliminating large break, loss of coolant accident as well. And that's a similar approach that we've taken with PRISM, where we have passive safety and eliminating loss of coolant accident. In terms of the second question on the environmental impact, both our SMR designs are designed to minimise and prevent the release to the environment from a severe accident. That's pretty much a standard approach for meeting the regulatory requirements, which we must do. And that's the approach that we have to take in that case.
Thank you. Mr. Song, please.
The regulations for the nuclear power plant are focused on the consequence of the accident, such as the maximum dose rate at exclusion boundary. This means SMR designer can achieve the equivalent safety goal by cheaper and simpler facilities, because the benefit of the small reactor for the safety is the small radiation source. The consequences of the accident might be lower than the larger one. Because SMART applies the same regulation basis as the large nuclear power plant, I can say that SMART is safer than the large nuclear power plant. The integral type reactor and closed loop of passive residual heat removal system also make it possible to reduce accident propagation and consequences. SMART design considers systems for the severe accident which has extremely low possibility to happen. SMART adopts the passive containment pressure and the radioactive material suppression system, including the passive hydrogen control system. But a backup containment spray system is prepared for the severe accident mitigation. By the Korean regulation issued at the end of 2017, the accident management plan is prepared for not only for the design basis accident, but also for the severe accident management. This plan includes evaluation of design for the prevention and mitigation of the severe accident occurred by multiple failure, natural disaster beyond the design basis, or aircraft crash.
Thank you. Tom, please.
Yeah, thank you. As I mentioned, the small cores and the simplicity of our design yields a remarkable safety case. Essentially, there are no credible postulated events that can cause fuel damage in our design, period. That results is indicative of a core damage frequency that we're talking about that's approaching 10 to the minus 10th, or a probability of occurrence of core damage in a module of 1 in approximately 3 billion years. It's a remarkable figure. And when you compare that to the advanced designs that are licensed to and achieve levels of CDF of around 10 to the minus 7, we're 3 orders of magnitude improved upon that. So what does that mean in practical context? Well, in the case of a Fukushima type event where the station loses all power, the Nuscale module, with being smaller and scalable and has fully passive features, and the fact that the power modules are actually in the ultimate heat sink of water, that on loss of all power, those units will shut down and cool for an indefinite period of time, not 72 hours, not 7 days, an indefinite period of time with no operator action needed, no need to restore AC or DC power, and no external water needing to be added to that pool. That's a remarkable feature. Secondly, the NRC recently concluded in their approval of a topical report that the Nuscale's design approach establishes the basis of how our design can be safe without the reliance on safety-related electrical power. So essentially, our design needs no 1E power. And I don't think there's any current design out there that is licensed to not require 1E power for its operations. That's, as far as we know, is a first for the nuclear industry. And then lastly, that strong safety case in terms of the environmental impact. You know, it's important for our design to be able to be sited near demand centers for the offtake of that electricity and that heat, and also in areas where the population densities are probably higher than had been previously approved. Our small cores, small source term, less radioactive material, less release associated with that, results in our ability to justify the approval of a site boundary emergency planning zone. So this emergency planning zone ends at the boundary of our facility, not 10 miles out as currently approved by the NRC.
Thank you, Tom.
Thank you.
Alan?
Sure, yeah. So So first of all, I think we have to be very careful with this question. It was asked at a recent conference I was at, and the CEO of a famous operating utility took quite an objection. We have to ask safer than what? Hinkley Point in the UK? We are in a business where safety is critical. We can't ever be in a situation where we're suggesting to the general public that stuff we're doing today is not safe. That was the point of the CEO, which I agree with. So, that said, our approach to safety is we do meet all of the latest regulatory standards, and we do that throughout our entire process of design. We are doing, as I said before, ours is a requirements-based design, and part of that is designing for licensing. We also have to take cognizance of the risk of licensing and the fact that regulators understand certain features more than they understand others. So our approach is to ensure that we use proven methodology where appropriate, and we incorporate all of the latest design parameters that allow us to meet the latest regulatory standards. So that includes natural circulation, passive safety features, etc., which allows us to get extended walkaway periods. In terms of the environmental factors, our plant is designed to be zero discharge during operation, and again, in case of severe accident, we have a proven approach to containment, core capture, hazard resilience, and safety systems that have been utilised across the world and are the latest in regulatory standards. So, in summary, we use all of the latest regulatory standards, and our approach is to ensure that we do not introduce additional cost or program delay through the licensing process by ensuring that we take an approach which is comfortable to our regulatory authorities.
Anton.
Yeah, the nuclear power plants based on the Rhythm series reactors fully meet all the post-Fukushima safety requirements. And this high level of safety we achieve through a combination of active, passive, and inherent safety systems. And we think that smaller is really safer. Accident management may be more effective. If the core is not damaged, we may safely remove the heat from the reactor building without any time limits, and even in case of full loss of electricity and operation control over the nuclear power plant. The compact design of the Rhythm series allows to withstand much severe earthquakes. And taking these and many other considerations into account, the Rhythm series nuclear power plant's emergency planning zone may be limited by the borders of the site of the nuclear power plant. Answering the second part of the question, we presume the possibility of severe accidents in our design. We prevent the escalation of the event into severe accident with the control rods, with the soluble poison to shut down the reactor, and while the residual heat removal system will remove the decay heat from the reactor core. In case of LOCA, the water injection system will compensate the loss of water, the leakage of water. And the thick wall of the reactor vessel will keep the molten corium within the reactor. Water-filled caisson under the reactor provides the reactor vessel cooling, and all gases will be localized by the hermetically sealed envelope around the reactor vessel, taking in mind that the reactor vessel is quite small. And to achieve a long-term, safe, stable, and molten corium stabilization, we achieve it through the molten corium stabilization, hydrogen mitigation, containment integrity, and overpressure protection to mitigate the releases, any kind of releases.
Thank you. Last, Mr. Song.
Like Mr. Jae-Seung said, SMR should be designed is beautiful, but we should design it safe. This is another needed. For ACP 100, we designed integrated primary system. That means we can animate large lockup during accident. Another thing, we designed the SCP-100 with lower power density. It's easy to transfer the residual heat during the accident. And with small power, we can demand for heat remove by essential core cooling system and containment core cooling system. They can be designed by passive way, so don't need emergency electricity. And the safety systems for the small power can be arranged in a small containment in modular way. This is why we designed the small and modular. For the environment impact during the severe accident, we have several methods, including the diverse acceleration system, passive hydrogen combination system, passive reactor cavity flooding system, passive containment cooling system. By these passive systems, prevention and mitigation for the severe accident, like high pressure coke melting, hydrogen explosion, steam explosion, containment overpressure, containment bypass. These are all in the merit of the small and modular design, in merit of the passive systems. Okay.
Thank you very much, gentlemen. Question number 3. This question is from Mr. Gerasimos Thomas from the European Commission.
Distinguished guests, I'm very happy to be with you here today. From Euratom's perspective, there are 3 issues that would drive SMR acceptance in Europe. Are SMRs safer and easier to decommission than conventional nuclear plants? Are SMRs more promising in a European electricity market targeting 50% renewable power generation by 2050? Last but not least, how competitive will be the produced kilowatt hour and under which assumptions?
So a question about competitiveness, especially. I think safety you have already mostly answered. So David, would you like to start?
Yes, okay, thank you. Yeah, so very simple answer is very competitive. We'd probably go as far as saying that in the BWRX 300, we have the most economic SMR on the market today. And that is based on feedback from our customers and talking to those customers about what they require. And that is to have future nuclear that is competitive with gas. So our target for the BWRX 300 is to aim for $2,000 per kilowatt hour. And that really focuses on really driving towards a capital cost that will enable us to use that SMR to displace gas in the future. So it becomes the choice for us of achieving that goal to have low carbon nuclear electric. Now the assumptions that's based on is nth of a kind, and based on an assumption that that is going to be a base load generation. Clearly we have flexibility in the design to meet load following as well in the requirements, but those are the assumptions that we're basing that $2,000 per kilowatt target on. So that's really the focus of a design for us to do this, and the feedback we've had so far has been demonstrated by Dominion Energy deciding to invest in this design in the US, which is a great step forward and gives us the basis from which to move forward in the future. So, thank you.
Mr. Song?
Yeah. The costs of the electricity generations different country by country and area by area to construct the plant. For example, the cost of LNG plant may be different at which the plant is located. If the location needs the high cost for the LNG transportation, the electricity generation cost will be high. SMR may be competitive for the isolated area, and also it may be competitive if the lower construction cost can be achieved by mass production concept by the same design. The passive safety system is also helpful to reduce the construction cost because many safety class active engineering safety features are not required or can be replaced by non-nuclear safety class equipment.
Thank you. Tom, please.
So there's no sales unless we are a competitive technology, particularly in the U.S. with combined cycle gas. In fact, we have a project with our first client, the Utah Associated Municipal Power Systems, that will see our plant deployed in the state of Idaho with generating electricity in 2026. So how is it that we are doing that with gas prices so low in the U.S.? As I mentioned, we are one of the most developed in technologies in terms of design maturity, and we've done very detailed analysis of what the cost of our facility will be. The overnight capital cost for a first-of-a-kind, first plant in the U.S., a 720 megawatt facility, is approximately $2.9 billion. Significantly less than the cost of large nuclear plants, and based on a considerably shorter 36-month construction schedule. That equates to, on a per kilowatt basis, of about $4,200 per kilowatt, certainly competitive with large advanced passive nuclear. And these are not aspirational or targets. These are numbers that are based on actual engineering, detailed design, and have formed the basis of our commercial discussions with our first client. And that equates to, for that first project, a levelized cost of electricity for the 12-module plant of $65 per megawatt hour, clearly competitive with the client's competing combined cycle gas project in that same region. And we expect these figures, like what I quoted as are all first of a kind, we expect these figures to improve. Our technology in the NuScale power module has been specifically designed to be able to be fully factory fabricated, taking advantage of that repetitive factory fabrication aspects of doing that in the shop, and shipping those modules to the facility to be installed through normal assembly equipment on the facility. Lastly, we know that those numbers are good, they're competitive, but they're not enough, and we continue to strive for even lower overnight capital costs and operational costs. And over a year ago, we started a very detailed value engineering exercise that we'll see and has already resulted in the identification of significant reductions in capital costs and operating costs. One of the outcomes of that was our recent announcement of the uprate of our facility by 20%, which has improved the overall economics.
Thank you. Alan, you are next.
So our design is requirements-based, and the principal starting point for us was levelized cost of electricity. And we took the components of that equation and drove all of the design requirements from that equation. Now, our analysis of our business case in conjunction with some of our utility partners has shown that the sensitivity to LCOE is driven primarily by cost of financing by an absolute mile, secondly by construction period, thirdly by capital, fourthly by power, fifthly by operational cost, in that order. But it is by far and away more sensitive to the cost of finance. And to put that in context, some of our customers have asked for a UK export finance package, and with that we get a third off the cost of electricity purely through the cost of differential in the cost of borrowing. So cost of finance is critical to us, and that is driven by certainty. It's driven by capital costs, certainty. Any borrower wants to know that they are, any lender wants to know that they are going to get their money back. That means we have to absolutely do what we say we will do. We have to build this in a short period of time. We have to keep the capital cost down through all the techniques such as modularity and other methods. And we have to do that to the letter. We cannot afford overruns. Capital does feature in third, and our approach to reduction of capital cost is all about reduction of the actual plant itself. It is the whole power station, modularity of the whole power station, as I've mentioned, but then also reduction of the construction cost. And construction on site is where we incur most of the costs. So we need to both remove that cost by putting all of the activity into factories that we can. All of our power station above our seismic raft is built in factories, and we have to reduce the risk of construction. So we use the very small footprint of our power station to enable us to put a canopy over the construction site, and that completely removes any environmental impact of weather conditions during construction. So we both reduce the time frame, but most importantly, the risk, and that's how we get competitive LCOEs.
Thank you, Alan. Anton?
Yeah, when we talk about the small modular reactors and the nuclear power plants as well as at all, we shall talk not only about the electricity generation, as you understand. When we talk about the supply of heat, when we talk about the supply of desalinated water, and that is why this is not only about the cost of kilowatt hour. This is about the cost of all the products the nuclear power plant can generate. Our goal is to offer a competitive energy solution for the specific needs of the targeted sector of customers, which are looking for the small, reliable, and the flexible solution. This is not for any customer on the market, maybe not for those who are looking for the large power plants, either nuclear or conventional. This is for specific sector. And the beauty of nuclear power for countrywide and commercial use is in the low fuel dependency and the high predictability of the cost of the kilowatt hour. So it is not only about the cost, it's about the terms of the supply of this electricity. Adding here the long life cycle of the operation of the nuclear power plants, SMR solutions would undoubtedly be competitive with almost every conventional power plant. The cost, I agree that the cost of the nuclear power plant is driven largely by the capital cost. The cost of a kilowatt hour is also driven largely by the capital cost of the nuclear power plant. And the capital cost is mainly driven by the cost of finance. SMR shall bring the lower completion risks, the shorter construction period, and that is why the terms of financing shall be better, which will influence positively the cost of production of the kilowatt hour. We strongly believe that reaching the highest level of price competitiveness will be linked to the use of standard design, to the prefabrication of large pieces of equipment, and in the implementation of effective life cycles and the business models of working with the customers and selling the electricity.
Okay. Sir, please.
So, small and medium-sized reactor and large nuclear power plant have different targets, I think. SMR is especially for the, not only for the electricity. If only for the electricity, it can be competitive with large nuclear power plant. We know in the early stage of nuclear power plant construction, the power from the small to the to large to higher. So SMR is used for the district heating, electricity generation, and seawater desalination. It has a multi-purpose use, and SMR can be deployed near the user. This is due to its modular design and more safe. But large nuclear power plant can't be located very near the user. So that's the difference. That's a different target, and I think if we deploy the nuclear power plant near the user, it's suitable for the SMR, not suitable for the large nuclear power plant. In this way, by this way, SMR is competitive for the user. even it may be higher cost for per kilowatt electrical. Okay.
Thank you. Monsieur Salha, please. You.
Yeah, about this question of cost of kilowatt hour, that is clearly a very strategic question for a big utility, for a company which sell electricity. So the French SMR is going to be competitive. That's clear. It is key for it to be competitive with other dispatchable energies, I mean mainly gas, but also compatible with energy mixed, in which tomorrow we are going also to have significant renewable energy contents. So to make it competitive, we have four main ideas on which we are strongly working. First idea is to have a simple, standard, and proven design in order to avoid any risk and to take profit of all the existing development. Second idea is to put the stress on the construction period. The experience feedback of most of Generation 3 reactor construction has shown that it is the construction period which is difficult. So we need to stress on the modular construction to make a significant part of the construction inside factories in order to reduce this risk and to put certainty in the final cost of the reactor. Third idea is what we call multi-SMR plant. We strongly favor this concept of multi-SMR plant. That's to say, a plant which could be of the size of 600 megawatts electric total, with 4 units, in our case, of 150 megawatt each. With such a design, the CAERI effect is embedded. You have 4 reactor vessels. You have, in our design, roughly 25 pumps, 25 steam generators. So it means that the CAERI effect which had made the success of the French nuclear program is really embedded. And 4 ideas is about international cooperation and partnership. We strongly believe that international partnership, international licensing is a key driver for the success of SMR. And so we are open to this international cooperation.
Thank you very much. So, this was question number 3. Now we move to question number 4. It's going to be a lady, Sherifa Noor from Nuclear
Good afternoon,
Malaysia.
ladies and gentlemen. As the SMR is posing a lot of great promise, it also is facing some challenges similar to the larger power reactors. And we would like to share that the challenge is, on one side, the need to comply with different standards due to the different designs by different nations pursuing the design investment, and also the need to comply with different regulatory as well as legal and licensing process. And on the other side is the need for harmonization in order to reach economies of scale. So based on all these factors, ladies and gentlemen, my question is, how does it impact the announced cost? Thank you and bon appetit.
Bon appetit was for the members of the audience. For you, it will be later. Okay. Well, the need for harmonization between the various standards, the impact on cost, and so on. Mr. Song, would you like to start, please?
The impact of regulation on the cost would be very, very high and uncertain. But no commercial SMR has been constructed to estimate it quantitatively. To reduce this kind of uncertainty, it is very effective to pre-application license process, such as the design certification of US NRC or the standard design approval of Korean NSSC. SMART has a standard design approval at 2012, but as actions for the Fukushima accident, the fully passive safety system is adopted and has a plan for the approval of standard design change to construct 2 fork plants at Saudi Arabia, cooperating with KAERI of Saudi Arabia. Smart design adopts all current pressurized water reactor regulations. But we are very interested in the US NRC's position of the regulation change issues for NuScale design certification process. The target cost may have no meaning without the real construction. Korea and Saudi Arabia are trying to ensure the feasibility of economics through the construction of 2 fork plants at Saudi Arabia.
Thank you, Mr. Song. Tom, please.
So as I mentioned, we were the first advanced technology in SMR to be submitted to the US NRC for design certification review. And the NRC's had our application now for about a year and a half. And that review is actually going quite well. It's on schedule, and there are no licensing issues that have been identified that will impact the schedule to receive the NRC's approval in September of 2020. It is, however, a lengthy and expensive proposition. But it allows us to have amassed a considerable licensing basis. The NRC's process is fairly prescriptive in nature. We will be starting the VDR process in Canada, and we expect that with a subsequent review by a more performance-based regulator such as Canada or in the UK, that we will have a substantial body of licensing information that will be needed for us to successfully go through any regulatory review process at hopefully an incremental cost to doing so, with most of the costs having been spent on receiving those first 2 main major regulatory reviews. We certainly support any initiatives that are ongoing or contemplated that will harmonize the approach to the regulatory process so that the regulators, as we move into different markets, have a streamlined and efficient process that maximizes the use of information that's been reviewed and approved by these major regulators so that we're minimizing the cost and the time as we move into these other markets. And we certainly hope that and expect that in many markets that the customers and their regulators will use, to a great extent, country of origin type approvals, given that we will have received major regulatory review and approval, and that can only serve to help reduce the overall cost associated with licensing our technology in the markets that we move into.
Alan, please.
Yeah, I mean, I concur with everything Tom said. I think we all need much more harmonisation across regulators, and we welcome everything that is being done currently to bring that. We need to get the nuclear industry to a place similar to that of the aerospace industry that will make life much easier and cost-effective for all of us. I think there's 2 aspects of this debate around harmonisation. Yes, the regulatory position is hard. We are currently talking with the UK regulator around the GDA process and entering the GDA. But fundamentally, different regulators do have a different approach. We are designing our plant with the various different regulatory approaches in mind. Nevertheless, you know, the devil is in the detail when you get into construction in a particular nation. In terms of the design, there are things we can do in the design. One is not introduce technology for the sake of technology, which we know will create problems with certain regulators. And another thing that we're trying to do here, which is crucial for SMRs, it was raised in the video, we have to bring standardization to the plant. And our design, we've designed it so that the whole plant, all of the plant and equipment sits on what's called an aseismic bearing. That insulates it from the particular site conditions of any particular location. And that's critically important for us because that enables us to have standardization and commonality in all of our modules that sit on that aseismic bearing. We do not have to redesign them for any specific site conditions. In terms of cost, that's one of the key drivers for us. If we can't get standardization into our modules, then we will not get economies of volume, we will not get our factory learner curve, and that will that will damage the cost competitiveness of the product, which is the entire reason we're doing it.
Thank you. Anton?
There are obviously a lot of tasks related to the harmonization of the regulatory environment, and this is one of the major challenges currently dealt by the SMR developers and the international organizations. In the absence of the special standards for the small nuclear power plants, we are developing our current design based on the written reactor, based on the requirements for the large nuclear power plants. And our goal indeed is to harmonize the applied norms and regulation without any safety reduction. And with this in mind, we are working closely with IAEA and Russian regulator to develop the current design based on our small reactor. And the answer to the question which was raised is yes. We think that we need to work on harmonization. We need to develop new rules, new approaches to the regulation of the small modular reactors and licensing of them. And we need to develop new standards for those small solutions, and that would definitely positively influence the cost.
Okay. Mr. Song.
Like large nuclear power plant, SMR is in its first stage of R&D. First of a kind of SMR. It may be not economic, but I think by the cooperation between the countries, between the vendor countries, between the vendor countries, the regulation, the standards may be harmonized by different countries. I know World Nuclear Association, IAEA have some standards, have some technical documents related to the SMR. By this way, I think in near future, the cost for SMR may be lower, and for the supply chains, for first of a kind, maybe cost more than cost more now, but I think in near future, if SMR can be built in series, it can lower the cost. Okay.
Thank you. Monsieur Salha?
So licensing is really one of the most important topic we have to touch with SMR if we want to keep the cost at a low level. The question with SMR is that they have specific features, specific technical features, which are not the same as the one of the big reactors. And so we need new approach. And clearly, this new approach need to be international. We need to have a global international approach for licensing of SMR. So the IAEA at the moment is working on this topic. With the French SMR, we are also working on this topic. As you know, we are established in France and UK, so we are working also in France and UK about this topic of international licensing. We strongly also encourage an early discussion with the safety bodies in order for them to cooperate and to reach a level of perhaps not standardization, because the approach of the country are different, but a harmonization, a common harmonization. And again, we strongly favor close cooperation between the different vendors, between the different operators about these safety features of the SMR. That's the key of the success.
David.
Okay, thank you. So I agree with my fellow speakers here that this is really about harmonisation. It is a big issue for the industry, both from an SMR licensing perspective and large-scale reactor perspective. We are one of the few vendors that has licensed our reactor designs in multiple countries, but how we would have loved to have done that only once. If I take as an example the ABWR reactor design, that recently went through the UK regulatory process, which is the generic design assessment process. On schedule, it took 4 years to complete, and that is the 4th country in which that design has been licensed. So think about the cost saving that could have been achieved by doing that just once through some kind of international standard approach. And I know there are organisations like WNE's Cordell Group that is working on harmonisation and others, but this is an important area, I think, for the industry and the regulators to get together and step up the work in this area. From our perspective, we will obviously have to comply with different countries' regulations as we go ahead with licensing our SMR designs. But it's really making use of that country of origin information and the work that you develop in doing that design to make the best use of that.
Super. So we have now the last question. This is a question by Mr. Benjamin Frémaux. I've not missed anyone, yeah? Yeah, okay. Monsieur Frémaux? Okay.
At Institut Montaigne, we strongly believe in innovation in the energy sector. SMRs are big drivers of innovation in the nuclear field, but what could make these reactors more acceptable than large reactors? We know that acceptability, apart from cost, is a key criterion for the success of nuclear in the future.
Acceptability. That's also a big question. We shall start with Tom this time.
Thank you. So I mentioned the scalable and the economics aspects of the technology, but I think what we need to offer and what we have strived to deliver on is the flexible operations associated with our technology. Big units today are essentially large base load units. Some of them do load cycle, load follow somewhat, but primarily they are intended to generate large amounts of electricity. And certainly our 720 megawatt gross facility can generate large quantities of electricity. But that's not enough to meet our customers' needs. We want to present a solution that provides a suite of flexible operations, making it simple for them to maintain and operate, shorter to construct, using a lot of off-the-shelf equipment. For example, our power conversion system, the turbine generator condenser, the turbines are just in commercial turbines used in a number of industries, very simple, inexpensive, easy to maintain. The fully factory fabricated aspects of our design take all of that field work and move it into the controlled environment of the factory. Certainly, as I mentioned, we have the ability to site our technology closer to communities, closer to demand centers, so they can take advantage of process heat capabilities of the technology, microgrids. Certainly, our technology is suitable for small grids, large grids, and distributed generation applications. It's ideally suited with our individual modules to direct that process heat to an assortment of industrial applications, desalination, hydrogen production, etc. We've studied those. We've produced reports detailing how that would work. We can also provide highly reliable power, a feature that you're not going to find in others. With those 12 modules and essentially those 12 power supplies, we can provide 50 megawatts of electricity at 99.98% reliability over the life of the facility. That means that facility is only not generating that amount of electricity for just a few days over 60 years. That's an incredible capability. And lastly, we just presented the results of a number of studies examining the resiliency of our technology. Those were presented at the most recent U.S. American Nuclear Society meeting, where we identified a number of features, including island mode operation, first responder power, black start capability, resilience to cyber issues, EMP hardening, and resilience to loss of transportation infrastructure, capabilities that you're not going to find in other technologies.
Thank you. Alan, you're next.
Thanks, thank you. I'll answer this in 3 parts. The first part is acceptable to general public. I think that's an important thing for us in the nuclear industry. We ran a general public questionnaire and analysis last year in the UK, and that threw up some interesting answers for us. The first point that came out of that was that there is a population, and I think this is true of anywhere, small as it is, that will always be against nuclear. That's the world we live in. I think that population is decreasing, but nevertheless, it is still there. The rest of the population vary in terms of their support or not, but the primary driver that we picked up from our polling was that actually it's all about cost. The general public, fundamentally, in the UK particularly, are interested in the cost of electricity. It's not so much about safety. So we have to bear the general public in mind, and SMRs certainly help in cost terms. The second one is our customers. Our customers constantly say to us, look, what we want is the lowest electricity with the highest level of certainty. And that fundamentally means that they want to pay as little amount as possible to build the plant, and they want to pay as little amount to operate it, and they want to operate it with extremely high capacity factor. So we have to design the power station to do exactly what the customer requires, and it is fundamentally those principal requirements. And then the final one is governments, and we have to consider governments. And in certain Western markets, our home market, for example, one of the requirements of our government is that they do not want to have to put their hand in their pocket every time somebody wants to build a reactor. Therefore, fundamentally, any SMR power station has to be financeable on a commercial basis. That's absolutely critical. If it's not, if it needs government intervention, we're not going to get the market volume that we require to get a return on our investment.
Thank you, Alan. Anton, please.
Okay. Yeah, first of all, the small modular reactors have all the advantages of the large nuclear power plants: the low CO2 emissions, the low burden on the low dependency on the fuel supplies, secure and stable energy supply, the predictability of prices. But on the other side, the SMR plants are more affordable to customers. The budgets are lower, the financing is easier, the construction periods are shorter, the energy system integration is easier, and operation is easier. Nuclear power plants can be located in the very remote areas, very special areas with smaller install capacity within an integrated energy system or a distributed energy system. SMR is also a solution to decrease the cost of the development of grid infrastructure, which is quite important as these developments are quite costly these days. We talked a lot today about the very exclusive safety features of the small modular reactors. So we think that SMRs have all it takes to be even more acceptable than the large nuclear power plants in some certain cases. And that would make what can make them even more acceptable is minimizing the burden on our customers related to the ownership and to the operation of these nuclear power plants. How we can deal with this is through developing the new nuclear infrastructure requirements, the harmonized regulation, new standards, developing of effective business models and effective models of the sales of electricity to our customer. And of course, the successful implementations of the projects based on the small modular reactors, we need to have the successful track records on the market. And the last idea which we presented yesterday is to use the small modular reactors on the floating base. That would leave all the burdens on all the burdens related to the ownership again and to operation of the nuclear power plant far aside from our customer. And that would make it easier for the customers to get access to the advantages of nuclear power through the floating, very flexible and easy approach to bringing the electricity from the place it's produced to the place of its real need really quickly and quick.
Thank you. Mr. Song.
Okay. I will give you an example to answer this question. In northern part of China, there's an industry park. It need steam, need electricity, and need seawater desalination. So we asked them why not choose a large nuclear plant it said large nuclear plant should should located 10 to 15 kilometers from the center of from the user. But by this way, the steam it can be used after long distance transportation. So they said SMR with its safety and it can have a smaller emergency plan room, so it can be located near the utility. And another way, the utility, the industry park is in the stage of development. It need 100 megawatt electricity in 5 years, 200 in 10 years, or 300 in 15 years. That cannot be achieved by a large nuclear plant. A large nuclear plant is 1,000 megawatt electricity. The industry park only need a curve of electricity in 10 to 15 years. So that's the SMR is more suitable for these areas. In conclusion, SMR can be built near the utility. Another, SMR can be built in modular and increase by module in module. That's my okay.
Bernard, please.
Yes, I try perhaps to develop three main ideas about this question of acceptability. The first idea is we need to build on the specific features on the SMR. So they are small, so safety is easier, longer grace period, longer inertia, and they can be built by module, so it means that the construction cost can be kept in an easier way under control. So that's the first idea. Second idea is the question of the market. We need to identify the specific market of the SMR. As I mentioned, we strongly believe in multi-SMR plant, so something around 600 megawatts. So what is the market for these plants? First, a grid which is perhaps not so big as the one we have in our Western country. So that could be an advantage for these plants. And second, because of the size of the plant, the global investment cost is lower. So it means that these plants are affordable by mid-sized utilities. And we need to strive on these two features. And last but not least, the question of public acceptance, the global public acceptance. We must recognize, we, a nuclear vendor or nuclear operator, that renewable energy is developing now at a great speed and at a great extent, and that the future electricity mix is going to be a mix of dispatchable energy, just like nuclear, and renewable energy. And so it's quite key that in this landscape, SMR could bring some advantage in load following, in compatibility with a mix in which you have more intermittent generation, in which you have more storage. The three ideas.
Thank you very much. Nice perspective. David.
Yeah, so I have 2 points I want to make regarding the acceptability. The first one is cost. You know, our customers say to us that they want new nuclear plants to have lower life cycle cost of electricity, you know, that competes with gas. And that's where we're targeting with our BWR SMR. But also from as Alan mentioned, you know, from a public acceptance point of view, I think cost is very important. Safety is taken as read, and I think, you know, if you look in the UK, you know, often, you know, when we see in the UK, the media portrays the Hinkley project as being very expensive. Now, there are really good, compelling reasons why we need to be building the Hinkley project in the UK, to provide that low carbon baseload electricity. But what the public sees is how the media portrays this. You know, they see £92.50 per megawatt hour as being twice current UK electricity prices. And that's also compared with wind prices that have come out at £57 a megawatt hour. So this is what I think we've got to try and address as an industry, is how we are portraying nuclear. And SMRs can maybe help with that. You know, with the lower costs, particularly lower capital level of investment in these plants, that can help us drive towards that. The second point I want to make is really looking at advanced small modular reactors like our PRISM reactor, and that's really there to drive towards tackling the waste. And that's another industry area that we really need to start looking at for the future. Now, I know here in France there's been a very successful program of reprocessing, recycling MOX fuel, and looking at fast reactors in the future and development of Astrid program. But if you look around the world today, there is 300,000 tons of spent fuel that's sat in storage ponds. You know, other industries are focused around recycling, and I think the nuclear industry needs to start doing more on that. And that's where technologies like advanced reactors, you know, including our PRISM design, can help in the future.
You are opening perspectives for a next lunch debate. Mr. Song, you will be the last to answer this question.
Yeah. If we compare the cost of a single SMR with a large nuclear power plant, nowadays the electricity generation cost of SMR would be absolutely higher as long as the current regulations for nuclear power plant are met. But what happens if we compare the cost of equivalent output? For example, a 1,000 megawatt plant and 10 over 100 megawatt SMRs. And what happens in case that the total electricity grid is 1,000 megawatt for a certain area? A single large power plant cannot cover a small electricity supply system because proper size of the plant is about from 1/8 to the 1/10 of the total electricity of the grid for the stable supply. So the acceptability of SMR depends on the situation of the area to construct the plant. Another consideration is the option during the construction of 1,000 megawatt plant or 10 of 100 megawatt plants. 10 SMRs can be constructed step by step as electricity demand increase. If the demand is not increased as prediction, the construction plan can be changed. But a large single plant construction cannot be so flexible. So one of the important factors in SMR acceptability is construction time, which is much less than the large one.
Thank you very much. Ladies and gentlemen, I think we can give our guest speakers a big applause. You really played the game very well. So it's like a political primary, but I think there is room for all of these designs in your countries. And I think you've opened up some nice questions about replacing the 300 to 600 megawatt coal-fired power stations, the integration of SMRs in a decarbonated energy system, and the fact that these SMRs can help to adjust, to adapt to the intermittency of renewables. What I suggest now, because our guest speakers, they saw you eat, so I'm sure that they are a little bit hungry. Frankly speaking, me too. So I suggest, as we said at the beginning, we are going to move to the Workshop 2 lounge. Our guest speakers will be there. They will answer your questions. All of you who want to accompany us, please join us at this Workshop 2 lounge, which is, if you go out there, you just move right. It's the lounge next door. Thank you very much.